All right, now the next question is to find a context-free grammar for this language. Now, the language is all a to the I, b to the j, c to the k, so either I equals j or I equals k. Now people sent me an email saying, well, could it be both? And the answer is yes, or does not mean exclusive or. It's a different operator. So that means that we can set j equal to I, so we have a to the I, b to the I, c to the k, or we set k equal to I, which means we have a to the I, b to the j, c to the I, and we'll call this L1 and L2. And our language is then simply the union of those two. Now this language is inherently ambiguous, so it's impossible to find a grammar, an unambiguous context-free grammar. However, it's easy to find a context-free grammar. What we do is we'll let S1 be the start symbol for L1, and S2 be the start symbol for L2. And you have to, a string has to be in one of those. So we simply say S can go to either S1 or S2. Now, what happens here? For S1, let's look at what we have. We've got to have equal numbers of A's and B's with any number of C's hanging off to the right. So we'll start by hanging C's. This allows us to put as many C's as we want to the right, possibly 0 of them. Now when we get to T, the T will be the one that generates the A to the I, B to the I. So T goes to A, T, B, but I could be 0, so it has to go to the empty string as well. All right, now the language L2, the start symbol is S2. But notice that we have to do the outside part first. So A, S2, B, C. And then when we're through generating A's and C's, we allow it to generate B's on the inside. So B goes to little b, capital B, any number of B's, and also the empty string, because the number of B's, well, it'll have to end at some point. All right, now let's go over to problem 8. In problem 8, I want to get a PDA that accepts the Dyke language. Now you recall what the Dyke language is. It's all strings of matching brackets, or parentheses if you wish. But in order to make it easier to grade, I said to use A and B for left and right brackets. So this would contain strings like A, B, A, B, B, A, B, A, B, and an important string that I forgot to mention is, of course, lambda, the empty string, is also a member. All right, now, how would this work? We have a start state here. Of course, if the string is empty, we can go directly to here. There has to be a bottom of stack symbol initially, which I'll call Z. So if the string is empty, I immediately go there. Now, if the string is not empty, the next symbol will have to be A. Now, we're going to have a rule that we have to push A's onto the stack. We never push B's onto the stack. And when we see another A, we push it onto the stack, but when we see a B, we pop one of the A's. That way they match. When we're done, it should be, the stack should be empty. Actually, it should contain only the Z. So, if we see an A at the beginning and the stack is empty, well, really it has Z, we push AZ. In other words, Z goes back on the bottom. If, on the other hand, we read a B, then there has to be an A on the top of the stack. We pop it and don't push anything. If we read an A and there's an A on the top of the stack, we have to push the new A as well as the old A. So that way it maintains it. And then when we're all done with this, the stack will be empty. It'll have a Z, and we execute this one. Problem 9 is to write a DFA, which accepts the language described by this regular expression. Now what you can observe is the empty string is certainly in the language because it's got a star there. But what it does is that it goes out and returns to the start state any number of times. Each time it reads an A, then does one of these things, whichever one, and then reads another A and comes back. So it could be that it does the empty string, it reads an A, and then nothing happens, and then it comes back. On the other hand, you could use B. So it reads an A, reads a B, and then comes back with an A. Or it reads an A, reads a B, reads another B, and comes back with an A. Now this is a minimal DFA for this problem. A lot of people made the mistake of trying to put a loop in here that has these three labels on it somehow. That is not a legal way to describe. Even though you have the right idea, there's not a legal way to draw a DFA. Let's go to problem 10. We want to find a DFA for base 4 numerals for multiples of 4. Well, what does that mean? That means that since we're allowing leading zeros, a base 4 numeral for 0 could be the empty string. It could also be 0, or 0, 0, 0, 0, any number of zeros. Well, that means that the start state is the final state. And the 0, 0 here means that if you allow empty to be 0, then it has to end with a 0, 0. If you read another 0, you stay there. All right, now, if the last two symbols are 0, 0, and you read a 1, then the last two symbols are 0, 1. Now you must realize this could be an empty string, so this would be just plain 1, which is okay. Now, this state represents a residue of 1. This is a residue of 0. If I add another 1, then the last two symbols are 1, 1, which is a residue of 3. So I could relabel these as 0, 1, 3, 2. All right, now if I read a 1 here, the last two symbols are 1, 1, which means it has a residue of 3 when I divide by 4. Now, if I'm in this state and I read a 0, I'll go here, because it then is 1, 0. And likewise, if I'm in 1, 0, read a 0, I go back to here. Now, I have not put in all the arrows. If I'm in 0, 1 and I read a 0, where will I go? I'll go to residue 2, because the last two are 0, 1. Well, on the other hand, if I'm in state 1, 0 and I read a 1, I'll go to 0, 1. Well, I'm really not done because there's another self loop here. If I am in a state 1, 1 and I read a 1, then the last two symbols are 1. So there we go. This is then what the DFA looks like.